So welcome to the afternoon class. We'll be investigating the traveling salesman problem. And as far as the problem is concerned, let's think about, because the numbers that I get do not actually follow sort of the distances between cities. So let's think about cost of airplane tickets between the different cities. Instead of distances. Because for airplane tickets, it's not bound by geometry, so it's quite likely that to fly from N0 to N2, it costs you $92, but to fly to N5 first and then to N2 only costs you $56 plus $11, because there are many factors that go into cost of airplane tickets. So often going a further route, flying further, will actually result in a cheaper ticket than flying directly. So here's our problem then, and I asked you to work out what gen children should be for this state representation. So to make clear what we actually have to do, I'll move that up one. Also, children are sometimes called the successor nodes in a search. So we have the cities from 0 to 5. Correspond to the city N0, N1 up to N5. Right? My state is a list of and the order, so that provides the order in visited so far. So let's say N0, N4, N5. So gen children of this state should return what? That'd be 0, 4, and 5, right? What should be the output? What should be the output for gen children state? If state is equal to 0, 4, 5. And what that means is that we went N0, then N4, then N5. 1, 2, 3. That's not really the successor state. You could return 1, 2, 3, and then you would need to do some more processing. So this is sort of like half of the work that you need to do. So in the puzzle, even if you don't think about the representation now, if I have visited N0, N0, N4, N5, then what is one possible next state? What action can I apply? What can I do in the puzzle? N1, N2, or N3. Yes, so if I pick N1, then what will be my new state? Zero, 4, 5, 1, correct, yes. So what do I have to return? N1, 1, 2, 3, 4, 5, N4. JC, that is actually too complicated. Oh, excuse me. You could, I'm not sure why you need to have the list of 1, 2, 3, 4, 5 for N1, 0, 1, 2, 3, 5. So you could just remove N4. So if I pick N2, then what will my next state be? Yeah, no 1 though, because we had 0, 4, 5, so I have 3 options, right? I can go to 1, 2, or 3, so then I get 0, 4, 5, 2. Yes, correct. So N3 similar. So what should be the output of generate children? What should generate children for 0, 4, 5 return? No. Because it's supposed to return the state that we get to by applying all of the actions that are possible. Right? Children returns a state, not an action. If you return 1, 2, 3, then you just say those are the actions you can execute. But you haven't actually executed the action yet. You haven't actually represented in your state what will happen if you go to 1, if you go to 2, or if you go to 3. Yeah, that's right. So the output of generate children should be 0, 4, 5, 1, 0, 4, 5, 2, 0, 4, 5, 3. Because those are the 3 states that I can move to after I applied my actions. And the action that I applied is easy, right? It's just go to city 1, go to city 2, go to city 3. So I can get the last city that I visited too, by the way, by just going state -1. State -1 will be the last city that we visited. Okay, now write this in Python code. Write a routine that will return 0451, 0452, 0453 for any state. So now complete this. And then send me your solution. Also the other students, JC, Junqiang, Kul, Minhan. Okay, 5 more minutes to work on your generate children function, or 4 more minutes. So I need to know how many cities there are. Actually, yeah. So cool, that's about correct. Just not in Python syntax. It's actually shorter if you write it in Python. Because Python is one of the programming languages. One of the statements is always that it's almost like writing pseudocode. So it's very expressive. You can do lots of things in a small number of lines of code. Yeah, EE09, that is not quite right, because what you tried out, what you write should run, but it's not quite correct. You can use your cities, that's okay. But if you just write this, and then you call generate the children from what was my example, 0, 3, 2. Prob 1, it's prob 1, what did I call it? Oh, okay, we're not using numpy arrays, so I cannot use the comma version. I have to write it like this. Still error. I'm too used to using NumPy erase where that would be legal syntax. Now we have our problem here. Right, then E09, your code will return 145, which is not what we want. No, because we don't use 0, 1 to indicate whether the state was available or not. It's just the list of cities that we visited. So JC solution assumes a Boolean representation, 0, 1 representation, which sometimes is useful. However, in this case, it's not useful because we need to know in which order we went through the cities. So state is 032, not just 0, 1, 0, 1, 0, 1. Yes, for N0 you could do that, but then after how would you update this when you go from N0 to N1? Yeah, that's true. You could have a list of actions that you push forward. That you could do. So you could use a representation like N0 and then 0, 1, 1, 1, 1, 1. Those are that I can go to. And then your next state, however, what happens after you visit N3? So if you go from N0 to and then visit N1, then how would you represent this? That's possible. You can JC, you can take your solution and make it a full solution, but it and state 0, 1, 1, 1, 0, 0 is not good enough because I don't know which which city I went to first. I just know that I went to N1, N2, N3. Or you can say you can still go to 1, 2, or 3, but I actually need to go there. So you need to update your state information, not just the actions. Similarly here in the Jupyter Notebook right now, we're returning that we can go to 1, we can go to 4, and we can go to 5, which is correct, but we haven't actually updated our state representation yet. In fact, this is what we would like to do, right? After state 0, 3, 2, then the states that I can go to would be 0, 3, 2, 1 or 0, 3, 2, 4 or 0, 3, 2, 5. That would be the correct output for generate children. right? Because now I know I went to N0 first, then N3, then N2, and now I went to N1. Or here I went 0, 3, 2, 4. Or here I went 0, 3, 2, 5. And those are the only options that I have. So that's a good way to generate the children. Now, one thing that can be confusing in Python and many other programming languages is that complex data structures like lists are actually passed by reference, not by value, which means if you change them, you also change them in the underlying calling program. So let me just demonstrate that. So here, so list, and we started at 032, and then place the successors are 0321, 0324, or 0325. But now if I don't copy that state, then weird things happen, right? Then your output is this 032145, which is incorrect, and it's also the same for these three. Right? They're all the same now all of a sudden. The reason for that is because let me demonstrate it here. So you have to be quite careful if you modify lists. Make sure that here I call it with state, which is 032, but after I return, now my state is 032145, and this is 032124145. They're all the same now because what I pass into state is a reference, and if I don't copy it, I will just change the one list that exists there, the one list state. So that's why we need to copy the list. There's two ways to do copy. If you know copy, you can do this, or using list comprehension, you can also write it like that. X for X in state. That does the same thing. And now we have 032. Afterwards, our state is not changed and our children are correct too. Right? This is what I want the output to be. And then we have our A-star search algorithm. So I have an initial state now that I can pass in, which would be just a list with 0. What about our heuristic function? Well, there I don't think we actually have any. I certainly don't have any good ideas for a heuristic function. Uh, So there doesn't seem to be anything that we can use there for an admissible heuristic. So the only thing I can do is return 0, basically saying, okay, you're really close to the goal. So I just define a function that always returns 0. So now assume that your boss tells you to write a program because the company has to send people out to travel all over the world, and they want to use the minimum airline cost, the minimum airline ticket cost for their travel. And then you ask your boss, well, how many cities do they have to visit? And your boss says, oh, about 40. Then what would you tell him? He asked you to implement a computer program for that, and he wants to know how much resources you need, what budget, how long will it take to implement the program, how long will it take to run the program, and what kind of computer do you need. So the complexity is order n factorial, right? We looked at that before. So each salesperson has to visit about 40 cities, right? So your boss asks you to budget for this project. In particular, how long will it take you to implement it? Take to run the program? What kind of computer equipment do you need to run the program? So what do you answer him or her? Transfers? What transfers? The flight? Yeah, they need to have 20 tickets, 40 tickets. But yes, first you would need to ask what kind of tickets you can buy. So that's correct, yes. So good point. So assume that you know about the tickets. And then let's assume that you have all the tickets that you can buy in a 2D matrix, which tell you to go from city A to city B will cost a minimum of that much. So you've dealt with all the special issues with airline tickets, and now you just have a 2D matrix, just like this. Now you have exactly this information. So you know to get from N0 to N2, the minimum cost for the ticket you have to pay, or the exact cost for the ticket. You can always fly, it's always available, $25. Yeah, they tell you, the salesperson will come and tell you I need to go to N0, N3, N23, N99, all different cities, and then back to N. So I have to go to all of these cities, and there is about 40 cities that the salesperson has to visit. So the request is city 0, city 1, city 2, city 3, city 34, 22, and the length of the request is 40. Yeah, that's correct. It's 39 factorial. The worst case complexity would be 39 factorial, yes. So how long does it take you to implement the program? How long will the program run? And what kind of computer equipment do you need? i9 with a 39D Ti. That's a nice computer, but I don't even know why the graphics card. And how long will it run then on your i9? We're using iterative deepening A star, so memory should not be a concern. If you were to use A star search, then the amount of memory that you would need to use is also going to be roughly 39. Actually, the memory, you could optimize out the memory constraint. So for this particular question, the memory space is not a huge concern because the search space is very regular. It doesn't make sense to use breadth first search, so we could just use depth first search. Because every solution here will also be exactly at level 39, right? So it would be a very bad idea to use breadth first search for this particular problem because it's extremely irregular. All the levels, all the solutions exactly at one level, level number of cities -1, plus you cannot fall into a deep subtree because once you reach level 39, then or level number of cities -1, once you reach that level, you either found a solution And in this case, you did find a solution, but not the optimal one. Or you have to stop and signal failure. There's no way to go past level number of cities plus 1, number of cities plus 2. It's impossible to go there because you ran out of all the cities. You visited them all already. So we don't want to use breadth first search, definitely not. We can just run depth first search. There's no need to do iterative deepening. We can also run A* search with sort of an initial guess for the distance. But now, how long will it take you to implement the program? What kind of computer do you need, and how long will that computer run to find a solution? Because 40 cities is not that big, right? When you think about it, there's millions of cities in the world. But your boss wants to save as much money as possible, so he wants you to return the optimal airline ticket itinerary. Have we discussed previously a problem that also has factorial complexity in this course? It's not quite 39 to the power of 39. It's 39 factorial. 39 factorial is much less than 39 to the power of 39. However, you're correct in specifying that this is a difficult problem. That's why they gave it to you, because you are the AI researcher. Yeah, it's the n-queens problem. Very good. And what did I say about the n-queens problem? For the n-queens problem, the largest solution found is 27. N equals 27. And that was done by the Q27 team. Which I think they're from Germany, Leipzig, if I remember correctly. So another problem that has factorial complexity is the n-queens problem. The largest n for which the n-queens problem could be solved is n is equal to 27. This was done by the Q27 project. So think about this. That means that the n-queens problem, which is a very popular problem in various researchers, optimization problems, many researchers have worked on that. For centuries to come up with efficient data structures and algorithms and heuristics. And after all this time, the best we could do, solve it for a instance size, problem instance size of n is equal to 27. So after many years of research, forgot the guys. And they managed to run it, or they ran it on special purpose FPGA hardware, especially programmed for this project. And they had, let me check how many boards they actually used. 1, 2, 3, 8. Devices. So 1, 2, 3, 4, 5, 6, 20, 26, 30, about 40 FPGAs. Running for over 1 year. And this included advancements in the algorithms as well. So there is absolutely no way you will be able to solve n equals 40 in the traveling salesman problem using a search approach. And I will give you 1 billion i9 computers and you still won't be able to solve it. Because that problem for n equals 40 is it's So we solve it up to 27, up to 40. That problem is this much harder. Than Q27. It's like solving billions and billions of these Q27 problems. Whereas in reality, you won't be able to solve Q27 with the hardware that you will have available, right? So the best you could hope for, I guess, would be about 20. Even that is quite high still. That means that you're running, you would think that you will probably be about 1,000,000 times as efficient as the stack of parallel FPGAs running for 1 year. So in that case, that would mean so if you go to Q26, then you only need to be 1/27th as fast as them. You can probably do Q billion times slower. That'd be about to this. So that's about 1, 2, 3, 4, 5, 6, 7. Yeah. So about Q20 you can do. Right. But the traveling salesman, they actually have the same information for the traveling salesman problem. And this is also a very well-studied problem where people have thrown a lot of computing hardware at it. The exact solution is up to, they say, about 20 cities. So maybe you won't be able to do Q20, but Q18, Q17 would be 18 times 19 times 20 times slower. So that's 6,000 times slower. 17, yeah, Q17. Or for the traveling salesman problem, if you tell your boss, really anything past 17 is extremely ambitious. 20 is the largest that people have actually solved so far. So 40 is ridiculously out of reach. On the positive side, your boss is not going to be happy to hear that, right? On the positive side, it'll take you about an afternoon to implement this. The only way to solve a problem of that complexity in a reasonable amount of time would be if quantum computers, if you use a quantum computer, then possibly, but that is not clear. Nobody really knows what they can and cannot calculate, and whether you can take the traveling salesman problem and map it to a quantum computing entanglement problem is not known at the moment, as far as I know. So at the moment, it's completely impossible to calculate this for cities up to 40 using a standard search approach. You can increase the, if it's a Euclidean space, you can improve the algorithm, then you can actually solve it up to branch and bound algorithms were able to do it for 40 to 60 cities. So for finding the exact solutions to this problem, really returning the optimal solution is not possible. Your boss is not going to be happy if you tell them that, right? So what can you do? Split that up in 2 slides. So this is actually the triangle inequality version of this problem, where we can solve 40 to 60 cities. But again, this is usually custom built hardware running for years to find a solution. So not something that you can install on your company network very easily. So let's first run and see the performance of our search routine. But we're not going to go up to n equals 40. In fact, we're going to stay way below that. We'll just do it from 2 to 10 cities maybe. So there's no real heuristic function that we can use that comes to mind. Then let's see. So I need to have at least 2 cities, I guess, before I can actually visit any. And I'm just going to run it up to 4 to make sure that mechanics are in place. So I create a problem for this many cities. And my initial state is then that I always start in city 0. Now I don't want to pass AX here. And right now, I don't want to look at the number of, I guess I could take the number of nodes. Okay, let's try this. State to string. Ah, yes. Frames. Okay, there's a bug there. I don't want to plot. Okay. It should be prob 1, not prob. State to string. Hmm. And I copy and paste the other one to a soft and gen children. And there will be prob for the problem. So gen children should have returned, but doesn't put in. return children. That should be correct. Should be initial state. Print current state. So, I want to return the child state and the action that was executed. So gen children here should return the new state and also the new action that we did. The only action that we can say we did was add CDI to it. So yeah, then we have this. Action map we don't have because we're just adding children cities. So the action map was here. So okay. So we expanded 2 nodes and we found a solution here. To start from 0, we go 0, 1 and then 1 back. So now let's see if we go, YS3 is not known. And I print out the problem before we solve it too. So here we have a problem 0, 1, and 2. So the distances are 0, 31, and 70, and 39. So this is N0, N1, N2, N1, N0. Okay, so let's see what we calculated. There's two solutions for 3 cities, and it returned 0, 1, 2. So the total cost there will be from N0 to N1 is 31. From N1 to N2 is 39. So the total cost there would be 70. And the other way would have been from N0 to N2, which is 70, plus N2 to N1, plus 39, which is 109. So we did find the better solution there, the faster solution there. Now let's see. And the number of nodes. 5. Okay, let's be a little bit more adventurous. Let's go up to 6. Actually, I haven't, I just counted 1, that's why, yes. Forgot to add the cost here, the new state cost. So I need to have a function that actually calculates the cost of the traversal so far. And that would be that we have to calculate here. So we need to add the current cost of the state. So that would be the current cost that we had plus the cost from moving from state -1 to new state -1. Right? Because now we added one more city. That city should be in new state is not child state -1. So it's this additional cost is the cost of going from the previous, actually no, I can do it like this, child state -2 to child state -1. That should be the same. and that's the new cost that we add, the additional cost. Or even better, to make a function here, I think. Well, let's try that. Cost, so that's our new cost. The state cost here would be state cost plus add the cost plus hval is a new state cost, and here cost so far is this plus that without the heuristic component here. And now we found other solutions, not just 0, 1, 2, 3, 4, 5, because before it was just adding 1 every time, so it didn't matter. It was just a matter of the level that we were at. So let's have a look at zero, 2, 1 for which problem? So here our problem is 0, 22, 12, 22, 0, 70, and 12, 70, 0. And the solution that we found is 0, 2, 1. 0, 2, 1. Start at 0, we go to 2 is 12, plus, then we go from n1 to n2 is 70, is 82. And if I go the other way, then I go from 0 to 1 is 22, plus 70, so that's 99. So that's also seems to work. It's the lower solution, the cheaper cost solution. Then we have a more complicated one with 4 values. Zero, 17, 79, 36, 17, 0, 85, 23, 79, 85, 0, 79, 85, 0, and 81. And then 36, 23, 81, 36, 23, 0, 81, 0. And the solution that we find is the solution that we find is 0.132. 0.132, so that cost would be from 0 to 1 is 17, plus from 1 to 3 is 85, to 3 is 23, from 3 to 2 is 81, so that gives me 104, 114, 121, and if I go any other way, 17, 23, and then I have no more choice. 36, 23, yeah. Okay, 0, 2, 79 plus 1, 1 to 2 is 85, so that's already above the limit. So yeah, okay, that's correct. I now will just record the number of nodes. I'll turn off verbosity and collect the number of nodes up to 10 and then just plot them. So we can see our exponential complexity there already. Oh, how come there's two plots? Fig. Oh, and I don't want to print out the solution. I guess I could. Yeah. It's another fig there somewhere. Oh. Okay, then we have this. TSP. Number of cities. Number of nodes. And ax.legend. So here's our A-star search algorithm, and number of nodes actually failed to find the solution because here 1500 nodes, so we'll set it to max nodes. So then again, you can see the exponential complexity curve shooting up there. And if we project it to 40, then it will be astronomically large. No way you can implement that. But I can go past 10 easily enough. Let's try 12 or 13. And actually, I need to plot two things. Yeah, okay. So I'll do that later. See, now we're topping already the maximum number of nodes that I want to allow. So okay, let's go 10 times as much. Okay, up to, for 12 now we have 175,000 nodes that we allow. And we leave it like that for now. Now we can run a little more extensive test later on. So your boss is not going to be happy if you just tell him that's impossible. So what would you propose? Well, actually, I sort of gave it away. Yeah, that's correct. Finding an approximate solution that's good enough in practice that we can find a lot faster than having to wait several billion years before we get the solution, right? So we would be happy to find an approximate solution, even if it's not optimal. So there are, for the TSP problem, because it's so well studied, there are solutions probabilistic algorithms that use randomness that find solutions within 5% of optimal for millions of nodes. for millions of cities, which would be even more ridiculous. 40 is already impossible, so millions of cities would be completely impossible. But by using various algorithms, you can construct, you can find solutions a lot faster, and also based on certain assumptions about the distribution of the solutions, you can prove that they are quite close to the optimal solution. So we want to, the best you can tell your boss is that you won't be able to find the optimal solution, but you'll be able to implement an algorithm that comes up with a pretty good solution in much faster time. But we want to, of course, not redo decades of research on traveling salesman problems. So what kind of algorithm do you suggest? If you look at this problem here, this is one example of the problem, and you start at n0, then as a human, how would you solve that problem? Because as a human, you also don't have a magical compute box that is able to calculate through n40 through 40 factorial combinations. Most likely, I don't know where that would exist. In fact, what you do have is you have your brain, which is a magical compute box, but it is much better suited to approximate solutions, pretty good solutions, than doing this kind of exhaustive bookkeeping necessary to iterate through 40 factorial combinations. So human chess players, for example, are not great chess players because they can evaluate many more positions than amateur chess players, but they're expert chess players. They're much better chess players because they know out of all the positions that could arise, which ones are likely and which ones are not likely. And the human brain is very good at sort of detecting those kind of features. So as a human, how would you solve this problem? Like even if you don't know anything about computers or artificial intelligence or Python programming, even if you don't know anything about those technologies, then how would you try and find a solution for the problem on the screen right now? So you start at n0 and then what? N4 or N3? So how come N4 or N3? Just because you like the number 4 and 3? Find the shortest route. Yes, we need to do that. We want to find the shortest route through all the cities. And trying to enumerate all possibilities is impossible because the smallest cost. Oh, I see. Okay. Yeah. That's a good idea. JC, that I didn't realize they were both 17, but yes, yeah. And what do we call this kind of algorithm when from our current state we take the action with the minimal cost? Greedy? Yes, that's correct. Excellent. Very nice. So that's called a greedy algorithm. And that's exactly what we want to implement for the traveling salesman problem. And we have used the greedy algorithm before in what puzzle? In the river puzzle? I forgot exactly where we used it before. We've used it once before. And as we can see, that, oh, the river bridge, the flashlight, two people crossing the river before the monsters arrive problem. And there we can see greedy algorithm didn't work so well. It resulted in a non-optimal solution that meant that everybody was eaten by the monsters. But that's because it's a puzzle. Actually, in lots of real-world applications, the greedy approach works quite well, or surprisingly well. Also in the traveling salesman problem. So actually I don't need all of this. So implement a greedy search routine. And I want to use the same parameters so I can call them in the same order. So initial, okay, cost limit doesn't really apply because I don't have to do an exponential search. The greedy algorithm, if I implement a greedy algorithm for the TSP problem, then what complexity does it have? Order So complexity of the search for the traveling salesman problem is order n factorial, where n is the number of cities. If I implement a greedy algorithm for the TSP problem, then what complexity will I incur? N? Yes, very good. That's exactly right. The complexity, because at every point, no, sorry, not quite right. Which I think I need to. Yeah, that's correct. So what is that in oh no, Let me see what I need to return here. Yes, exactly. It's n squared because I take a city, I move, then I have to check the distance to all the other cities that I haven't moved to yet. So at the beginning, I have to look at n squared cities, and then I have to look at n cities. Then I have n minus 1 cities left, n minus 2 cities. So it's actually 1/2 n squared, but that's taken. That constant factor is ignored. So we're looking at n squared complexity. Very nice. History I don't actually care about because I don't have to do any backtracking. Actions, I guess we want to keep those. Num nodes, sure. Max queue length is actually 1. I already know that. And min cut cost, I don't actually ever cut anything, so that will be none. So one state is not solved. The children are generate the children from the state, all the possible successors. Then for each one of the children, get the state and the action that resulted in that child. And then I don't need to keep track of all of them. So I better write a function to just calculate the cost of a state. Or I can also go state cost is equal to 0, because we start with first node. Then we get this. Then we get a child state and a child action. We look the cost that's incremented. H value. Child. Otherwise it's 0. Yeah, then we get the additional cost. And then while I iterate through the children, and here we get the, and you should try of course to implement your own version of the greedy search, but here we just have to remember what the minimum cost is. We iterate through all the children, and I also then I need to update my state. So that means state is equal to min cost state the minimum cost action is equal to the child action. Well, this is not solved and the number of nodes is less than the node limit. Now we have that. think that will do it. And then at the end, we need to return the state, yeah, the history, yeah, the actions, the number of nodes, max queue length, and min cost. Okay. If not min cost, break. Okay. Okay, then let's try and plot instead of A star search. Let's see if we can apply our greedy search. Cost limit, no cost limit, node limit, max nodes. Zero, okay. Actually, I add some print statements here first. I'll pick the same ones that I used here. None, how come we returned none? Oops, this is not quite right. Definition 072, current state H 0 5. Zero, 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 that's not right. Two and four. So why does this return zero? State. Problem definition, so two cities, and it says it found a solution in one node. So that's wrong. Current state H0, number of nodes 1, actions 0, and I also have to set the I also want to print out the cost. Other way around. Two, three, and the actions. Yes, so the actions are from 0 to 1, 90, yeah, and then here only 9 to 92. Solution found. Ah, that's X and Y, right? That's that print statement here. Yeah, okay. So then let's try this out to, before we ran it up to 12. So then we calculate that. And now I want to compare the performance of the two solutions. So we have the greedy search, ys.1, append notes. So this is ys2. And I also want to show actually ys3.append append calc cost of state and ys4.append calc cost of state, because now with our greedy algorithm we're not going to get the optimal solution. So I want to see how much worse solution we actually get. So ys1 and 2 are the nodes, 3 and 4 are the costs, and then I actually have to define a function here to calculate the costs. For a particular problem. And let's see. Calculating the cost. So for I in range 1 to length of state, cost is 0. For I in range 1 to the length of the state, cost is cost plus prob state I minus 1 to state I, return cost. Wasn't happy with that. Yeah. Then let's try and plot this. So this would be the greedy search. And then three and four. And this should be AX2, 2, 2, 2, 2, 2, 2. So you can see here with our cost, actually the left side is the number of nodes, right? The computations that we did. The right side is the cost of the solution. And you can see our greedy algorithm actually does pretty good, right? The blue one is the best we can hope for. The red one is the greedy search. And you can see here it just messed it up a little bit. But it does do a reasonably good job given a runtime cost, which is basically zero compared to the cost of running our algorithm using A-star search or another kind of search algorithm for the traveling salesman problem. And in fact, people have analyzed this. On average, your greedy search will end up with a solution that is within 25% of the optimal solution. So in the scenario that I described, your best approach is really to tell your boss that there's nothing you can do for finding the optimal solution for 40 cities, but you can easily implement a quick algorithm to... Oh, that was still running there. And now it failed. You failed to generate the video on the previous slide. Never mind, we don't need the video there. So let's run it another couple of times. And I can turn off verbosity. To just make it print out less. So here again too, it very much matches the performance of the optimal algorithm. Right? The A-star search does just a tiny little bit better than greedy search. But the runtime is for the greedy search, even if we assume it's full n squared, then it's 144 compared to 300,000 nodes that I expanded for the A-star search. Of course, then the more cities you have, the higher the chance it is that your greedy search will find a local optimum, but not a global optimum. But again, the cost, it does a reasonable good job with a much simpler implementation, as well as a simpler, much faster runtime. So we can try and run it another one more, maybe 13. Of course, if you know that somebody's using greedy search, then you can easily misguide the algorithm to try and find a input that will make the greedy search perform very poorly. That is also given. So you can see we have a slightly more discrepancy, about 230 to 300. So that will be about 30% worse here in the worst case. So once you are faced with having to solve a problem, solve a search space that is so large that it's not possible to search it exhaustively, even with sort of tweaks and implementing it in C++ or whatever you want to do. None of that is going to be able to help you solve a problem with a complexity of n factorial and n is equal to 40. Just no hope. So unless you can come up with a much smarter algorithm, like n, if you do have the complexity of factorial, then 15, 16 is already pushing it. 20 is quite large. That's sort of the maximum you could hope for on a standard PC with a couple of hours of computation. If you have access to a supercomputer, then you can do slightly more. Maybe you can do 21, but that's about it then, or 22. Like you can see, the cost goes up very, very quickly here. This will be basically a wall that you cannot overcome with getting faster hardware or anything like that. Nothing is going to help you there. You do have to find approximate solutions, cut down. And in fact, most of AI research since mid-1990s has all been about the trying to reduce the amount of search that we have to do, coming up with good heuristics, using local methods like greedy search or gradient descent or hill climbing search, those kind of approaches. And also a lot of using probabilistic algorithms, finding solutions that are with 80% probability within 5% of the optimal solution. That's been a lot of the focus of more recent AI research. Okay, I think that's a nice graph to show. I can run it one more time, or you can run it yourself. So much more tractable. Bring that up one more. Let's put those. So we want to implement greedy search. And then let's see how we're doing here. Okay. Yeah, still reasonably good, within a factor of 30%. Given a much faster runtime. So a lot of the probabilistic algorithms, how would they actually work? Any ideas? Okay, good. Maybe enough word today for today. Then next class, I want to introduce a probabilistic algorithm to solve the traveling salesman problem. Okay, and I did share this with you already, right? Yeah. Okay, good. Then that's the end of the class for today. Then next week, we will have a class on Friday, which should be the final exam. And then Friday afternoon, I want to talk about the project. And the assignment. So next class is 22nd. Actually, let me check. So final exam is on Friday at 1 o'clock. And then we can discuss the project afterwards. And we have one more class on 9. That's not so